So let me now do a more complicated example, and then I'm going to conclude for today. We'll take a break, and then we'll get to our speakers. So here's an example where you've got a new drug that just passed phase 1 clinical trials. Okay? Hooray, it's safe. Now you want to see whether or not it's effective for a small population of patients. So it's going to cost you $5 million to run a very small phase 2 trial. It's going to take 2 years, and your best guess is it's going to be 40% probability you're going to succeed. Now, if phase 2 does succeed, if it achieves its endpoint, then you're going to need another $50 million for phase 3, which is a much larger population of people. And there, the probability of phase 3 succeeding is very high. It's 70%. But in order to do that, you've got to get to phase 2, right? You've got to get through phase 2. And finally, if phase 3 is successful and you meet that endpoint, at that point, you get the FDA to approve the drug, and your drug is going to be worth $150 million net. That's the NPV of all of your future cash flows. Okay? So assume a discount rate of 20%. This is now the important risk adjustment part that we didn't need to do in standard option pricing theory. Standard option pricing theory, all I needed was the risk-free rate. I didn't need to do any kind of risk adjustment or cost of capital because I'm doing relative pricing, 2 bottles of ketchup versus 1. Here, I don't know what anything costs, so I'm going to need to have a cost of capital. 20% is the cost of capital. So first thing that I tell my finance students to do, draw a timeline, right? So phase 1, this is where we are. We just succeeded. And now we're looking at $5 million to pay for the phase 2 trial. That's going to take 2 years. If that's successful, we pay another $50 million. And if that's successful, in year 5, payday, $150 million. Okay? And the probability between here and here is 40%. Probability between here and here is 70%. Now, this looks complicated, but actually it's not. It's actually pretty simple if you look at it one step at a time. And so the first thing to do when you're trying to analyze this is to draw that decision tree. So you want to look at all of the various different steps of what you're about to do. So here's how it's structured. This is time going across the horizontal axis, year 0, year 2, year 5. And these are the key milestones that you're looking for. All right, you're going to spend $5 million today, and with 60% probability, you're going to be up here, 40% probability, you're going to fail, and similarly, 70%, 30%. Okay? Start at the end. If we succeed with our phase 3 trials, that's a $150 million payday, right? So how does that look from the beginning of that interval at year 2? So we know that if I make $150 million, then the expected value of that, discounted at the appropriate risk-adjusted cost of capital, as of year 2, is going to be given by $60 million. All right, 70% times a payday of $150 million, discounted 1.20 to the 3rd power. That gives me the expected NPV as of year 2. Any questions about that? So I've effectively taken this branch and pushed it back 1 level. Okay, so that phase 3 trial is going to cost me $50 million. So my net, in this case, the expected value of my phase 3 trial, net of expenses, is 60 minus 50. It's about 11. Okay? So this is the value. And now if I take that and multiply this by 0.6 and divide that by 1.2 to the 2nd power, as of date 0, which is the date that I care about, this now is going to be worth $4.5 million. Okay? And now, if I look at what's happened here, a $5 million cost, $4.5 million risk-adjusted NPV, the bottom line is this is going to lose me $500,000. Do not do this. This is not a good project. So the fact that I can shut down here and here, it actually adds value. And so that's the implicit value of the option going back in time. But notice that nowhere did I actually have to use any kind of concepts from option pricing theory. All this is risk-adjusted expected value with a decision tree. So in the Merck case that we're going to ask you to look at this week, you're going to be just using this. You don't have to do anything with option pricing analysis, but the implicit idea going on here is that you're getting rid of the downside and are able to shut down, and that's going to create value. Any questions about this? So I want to do one more thing before we wrap up the first half. I want to show you how we can actually make this a bit more complicated and use more of this option pricing framework. It turns out that clinical trials aren't so simple. It's not just up or down, yes or no. You actually collect data from these trials. And so I'm going to assume that at the end of phase 2, you actually learn something about the magnitude of the treatment effect. In other words, you could have a phase 2 that ends spectacularly well, where the patients all get better, nobody has any side effects, and it's much better than you had expected. That's one possibility. The other possibility is that you met your endpoints, but there were some toxicities, some adverse reactions, and the statistics don't look great. But in both cases, you might say that you've passed, right? So let's get this to be a little bit more complicated then. Let's suppose that there are two different kinds of phase 2 outcomes. Either phase 2 went really well, or phase 2 went so-so. And in those two cases, phase 3 looks actually quite different. So if phase 2 goes really well, then it turns out that your phase 3 options are 70% worth $350 million and 30% worth nothing. So that's better than what we had before. Before we had 150 versus nothing. If phase 2 went really well, then the phase 3 trial from that good phase 2 outcome will be 350 or 0. But suppose that phase 2 went so-so. If phase 2 went so-so, then I'm going to assert that now your phase 3 will look like this. $50 million value versus 0, right? I mean, if the treatment effect is not that large in phase 2, you're not going to really expect that it'll do much better in phase 3. Maybe it will. Maybe you just had a bad sample of phase 2 patients. But most likely, the betting money is you're not going to do as well. So suppose that we actually got this information instead of just this one readout of phase 2, yes, 150 or 0. We now have two different possibilities for phase 3, right? Let's go back and do the math. If you go back and calculate the expected risk-adjusted cost of capital and calculate the discounted value going back here and going back here, look at what happens. What happens is you have these two different outcomes. This is when you have a good phase 2. Your phase 3 is worth $91.8 million. And this outcome is when you have a so-so phase 2. Now the NPV of a phase 3 is negative $29.7 million. So don't do it. Don't do the phase 3 trial in the case where you don't get strong evidence from phase 2. This is an example of how real options can add value. So now I'm going to get rid of this. I'm now going to make this 0. And if I make this 0 and I calculate the value, basically what I'm doing is taking the maximum of the two possible phase 3s depending on how phase 2 did. And so you can actually see that this can actually create real economic value. In this case, now the project is worth $12.7 million versus minus $500,000, just from the fact that I'm using additional information along the way. Now, you can see how this can get a lot more complicated because there are many different decision points, many different readouts, and many different interpretations. So your decision tree may look like a god-awful mess. It may look like some 100-year-old oak tree with lots and lots of branches and things like that. But it's actually very mechanical. And the beauty of this decision tree is that you and I, we can have a conversation now. Once we put this out there, scientists and business people can have a rational conversation about whether or not to progress a particular trial. The scientific merits may be really compelling, but if it's going to give you a negative $29 million NPV, who's going to pay for that? I'm not suggesting that it shouldn't be paid for. There are many cases, including cases that large pharma companies have decided to take on negative NPV projects for other reasons. Merck is a good case in point. Under Roy Vagelos' leadership, they decided to pay for and essentially cure river blindness using a particular drug. That was definitely a negative NPV project, but they did it for ethical reasons because they could do it, they had the technology, they knew how, and they felt it was the right thing to do. So with this framework, it at least allows you to have the conversation of what it's going to cost you, what it's going to cost the firm. You may not like the answer, but at least it provides a rational way of discussing it. So the bottom line here is that if you have this additional information, you proceed, and the value of the optionality we know is basically this. It's being able to get rid of this $30 million hole because you've got a much better readout on what the likely outcome is going to be. The other thing to keep in mind is that decision trees are really, really easy to set up in Excel. And so that's actually important because you want to be able to implement these ideas. And sometimes being able to go through and take a look at column by column what each of the nodes of the trees will give you, it's actually a very powerful way of having business conversations and incorporating the science directly into the business considerations. It's pretty difficult to do it otherwise. I don't know of any other tool that can be as facile in making all of these different components come together.